by Go, which are called slices. And this is how we can make a slice using an array. And if we try to run this, we get this result of 3, 5, and 7, because this syntax, this indexing syntax that we use to create a slice out of an array, this is how it works. In the first part, we have a opening square bracket. In the first part, we have the starting index, and in the next part, we have the ending index, and this is excluded. This is not part of it. So since the starting index is 1, we start from here, and the ending index is 4. So 0, 1, 2, 3, 4, and we exclude it. So this is the range 3, 5, 7, and that's what gets printed here, 3, 5, 7. Now a slice is a very special data structure that is available to us. It is very flexible and it is very useful, and its mechanism is a little different than our typical arrays. And slices are also called a reference type. They are called a reference type because a slice has always some backing array. A slice only refers to an array that is working in the background. So if you want to understand how it all works, let's imagine this. We have an array. Let's see. This is the array. And we have different indexes of the array. And let's say we have numbers 0, 1, 2, 3, 4, 5, 6. Now this is an array in Go, and its type will be the first part 1, 2, 3, 4, 5, 6, 7. 7 integer. This is the type of this array. Okay. Now, if we create a slice, now how slices work is a slice has 3 parts to it. So you can imagine a slice. We have a slice, and a slice has 3 parts. One is the length of the slice. Second, its capacity. We'll come to capacity soon. Capacity. And the third is a pointer. And a pointer to the first element of the array, or a pointer to the first element of the array that the slice is pointing to. So in this case, it does not have to be 0. It can be this also. It can be 2 also. So now a slice, when we have a slice, it has a background array, and this slice points to this element. So this first element of the slice is 2. Now the capacity of an array, the capacity of a slice is basically starting from the element the slice points to up to the last element of the backing array, not the last element of the slice. So in this case, the capacity can be 1, 2, 3, 4, 5. The capacity is 5, and the pointer is 2. That's what it points to. And what is the length? Now length can be the same as the capacity depending on how we sliced it out of the array, or it can be different than capacity. So in this case, length can be, let's say, 3. Capacity can be 5, length can be 3. Length can also be 5. Now it's all a little confusing. Now we will see a couple of examples and it will become more and more clear. I've just shown the figure here so that we can come back to it and we can imagine and visualize how it all works. Okay, so let's get to the example first. Now here we have an example. We have an array. Not a slice. We have an array whose length is 4. Now let's picture this. Here. We have this array. Okay. Sorry. Let's picture this. We have an array like this. Okay. And these are the elements. So we will start the indexes from top to bottom, 0 to 3. Okay. And in the first index, we have John. In the second index, we have Paul. Third, George. And then we have Ringo. Okay. This is 0, index 0, this is 1, this is 2, this is 3. This is the array that we have. It is a fixed size array. We cannot expand it, we cannot reduce it, we cannot do any kind of changes to it, but we can slice it. Now let's understand how slices work. in this example, what we are doing, we are constructing a slice A, and it is slicing from this array from index 0 to 2. So now the slice A will have 3 parts, as I said. First part is the length. Length will be, since it is slicing from 0 to 2, so let's say 0, 1, 2, 3. 0 to 2, and since we exclude the last part, so the length is 2. Okay, and second part of the slice is capacity. You'll be more clear about the capacity after we go through some examples. For now, let's just stick to the concepts. Now the capacity, as I said, is starting from the first element of the array that this slice points to, which is 0, up to the last element of the backing array, not the last element of the slice. Now, how much is the capacity? The capacity is 4. Since we start from the first element, the capacity is the same as the backing array. Now we have the capacity 4. And we have a pointer. It has a pointer which points to John. Basically, this part, John. Okay. Now we have A. In the same way, we have B. B, what it does, it starts from the second index, basically index 1. So now we have length as, it starts from this index, and it goes up to the last index, third. And since you exclude the last one, the length will be 2, the same way. And the capacity is starting from the first element of the array that it points to up to the last element of the backing array. Now the capacity is 3. And the pointer is, what is the element that it points to? Is Paul. Okay. This is how the physical representation of an array and the slices that come from it looks like. Okay. Now in this example, what it is trying to do is, it is doing in the array, in the slice B, it is changing the first index to XXX. What is the first index of the array B? Since it starts from here, it is trying to change the first index, the value of Paul, this part, to XXX. So now the value of Paul has been made XXX. Okay. And now we are printing A and B, and we are also printing the backing array. Now let's understand why are we looking at this example. Since we know slice is a reference type, and now you understand why do we call it a reference type. We have an array which is a fixed type, and we cannot expand it, but we can slice from it. So we have 2 slices from the array names. One is A, another is B. Now this array, the array names, the slice A, the slice B, all 3 of them point to the same thing. All 3 of them have the same value. Names is the actual data type, and the slice A and B point to names. They are sliced from it, but they point to the same data. That's what you have to understand. A slice does not have the data for itself. It points to an array. It points to a backing array. In this case, all 3 of them have the same value in this position, which is Paul. And now any of them, so in this case, B has tried to make this value as XXX. Now what happens? This will change for all of them. A, B, and names. Now, if we run this, let's see what we get. Let's clear this and try to run this. You can see in the first print statement here, we are getting John, Paul, George, and Ringo. And after slicing, we are printing the value of A and B. And the same way, we have John and Paul and George. Okay. Nothing has changed up till now. The moment B has changed the value of Paul to XXX, now we have printed A. Now A has John and XXX. We have printed B. B has XXX and George. And we have also printed the names. There's John, XXX, George, Ringo. Now since one of the slices changed the value in that index to another value, that value got reflected in all 3 of them. The backing array that contains the data, and all the slices that point to that array. Okay, that's the point that this example is trying to make. Whenever a slice which is pointing to some array changes some value in that array, the value of the array changes, and all the values in all the slices that are pointing to that array, they also change. We don't always create slices out of an array. We don't have to declare an array and slice from it. We can directly create a slice. Go provides us the ability to directly create a slice, and in the background Go will create a backing array and it will give you a slice which points to that array. Okay, and that's how it will work. So this is the syntax using which you can directly declare a slice. You do not have to declare an array and slice from it. You can directly declare a slice, and this is called a slice literal. We are literally declaring a slice in one line. Okay, we have a variable declaration pattern here, with the colon equals to, and here we are saying it is a slice since there is no number in between the square brackets, which means it is a slice. That is the indication. That is the difference between an array and a slice. In an array type, you will find a number which is the size and it is part of the type. And in a slice, there is no number. It is a dynamic array. Okay. So this is a slice and it is a slice of integers. And here we are providing the values during the initialization phase. And here we are printing it. In the same way, we are creating a slice of booleans. So we can only store true and false. We cannot store any other data type in a slice or in an array. It is a collection of homogeneous data types. In the same way, we can also make a slices of structs. So this is how the syntax looks like. You write a pair of square brackets, then you define the type. In the same way, here we have defined the type. You can integer, boolean, or a struct. If it is a struct, you have to provide the type of the struct. And the type of the struct is this. It has two fields, I and B. I is of type integer, B is of type bool. Now, right after, since it is an slice literal initialization of type struct, okay, we have to provide all the values that goes inside this slice of structs. So we can provide, we can follow this pattern. 2 will get assigned to I and this true will get assigned to B. Same way, all the structs are initialized in these slices and then we can print it. So let's run this and see how it looks like. Okay, and we can see all the slices that got printed here. And this, since this is a slice of structs, we can see all the structs being printed here in the Go's format. Now another thing is you can also slice from another slice. Here we don't have an array here, but you can create more slices out of this slice. Okay, and also we can modify, we can make changes to this syntax. We don't always have to provide the low bound or high bound. We don't always have to provide the start index and end index. We can leave one of them and the other range will be implied. So for this case, we are saying we are slicing from the first index, from 0 to 2. And here we are saying we are slicing from index 1 up to the end. Okay, those things are implied here. And we can run this and see the example how it looks like. So we have 3, 5, 7 for the first, then 3, 5 and 5. Here for this we have 3, 5, 7 because we are indexing from here up to here, from index 1 to index 4. So we are taking 1, 2 and 3. That's why we have 3, 5, 7. From this we have this 3, 5 and 7. This is the value that we have. Then we can slice it again, and when we slice it, we are slicing from the first position, from 3 to the index 2. So 0, 1, 2, and we exclude the 2, so we have 5. We have 3, 5. That's why we get 3 and 5. And here we take this slice and we slice it again, and we are slicing from the first index. So this is index 0, this is index 1. So we are taking the first element is 5 and up to the end. And since this is the last element, we end it here. And that's why we have 5 here. That's how slicing works. And you can slice from an already existing slice. You don't always have to slice from an array. You can also slice from an existing slice. Now in this example, we take a look at lengths of slices. So what we are doing here, we are defining a function called print slice. What it does, it takes a slice of integer as a parameter, and what it does, it tries to print it. And how does it format it? It is taking the length of the slice and it is taking the capacity of the slice, and it is then taking the slice itself, and it is printing all three of them in this format. Okay, that's what this function does, and we use it here. We create a slice using the literal syntax. We say it's a slice of integer, and we provide all the integer values. And then we do the print, we call the print slice function, which displays the length, the capacity, and the value of the slice itself. The same way, what you're doing here is we are slicing from the start, because we have left the starting index from the start up to the 0 index, which basically means the length of 0. We don't want any elements because the last element is excluded, and we are starting from the start. We have now 0 elements. We don't have anything. We have an empty slice. Okay. In this print statement, we should have an empty slice. Now let's picture this, how it exactly works. So for the first, initially what happens, we have initialized a slice. So we have initialized a slice. So we have a slice here, and it has a backing array. But for the sake of this example, let's imagine this is the backing array, because when you initialize a slice literal, then the length and capacity of the backing array is the same as the length and capacity of the slice. So you can imagine this slice as the backing array. Okay, now we have 2, 3, 5, 7, 11, and 13. And these are the slots, is index 0, 1, 2, 3, 4, and 5. Okay. And this is what S looks like initially in this print statement. So for this print statement, what will be the length? The length will be the initial length. This is 6. And what will be the capacity? For a slice literal, the capacity of the slice is the same as the capacity of the backing array. It has a backing array which looks exactly like this, because we initialized a slice using the literal syntax. That's why and that is the reason for the first print statement, we get length as 6 and capacity as 6. Okay. And when we print the slice, this is 2, 3, 5, 6, 2, 3, 5, 7, 11, 13, all the elements of the slice. Now moving on. At this point, what happens? What happens is we are saying we are starting from the start. Okay. We are starting from the start, but we go up till the 0 index. And since the last bound, the higher bound is excluded, we exclude the 0, 1. So in that case, we don't have any elements. So this is an empty slice. But what is the length here? For an empty slice, what is the length? Length is 0. Length is 0. As you can see, length is 0 because we don't have any elements yet, because the higher bound you mentioned was 0. What will be the capacity? Now, as we know, the capacity is the first element that the slice points to. In this case, it is 2, the index 0, up to the last element of the backing array. And this is the backing array for this slice. And that is the reason we have the capacity of 6. We have capacity of 6. And as you can see, the capacity of 6. Starting from this to this, we have 6 slots. The capacity is 6. Then what happens? At this point, we are saying we are starting from the start. For this slice, this is the backing slice. Okay. And this slice points to this. Now what happens? The starting, we are starting from the 0, 1, and we are going up till 4. And we are going up till 4. Now we are extending the length. Length was 0 here. And since we have a capacity of 6, we can extend the length. What happens when we extend it? From 0, we go up till 4. Now this is 4. So now we have 2, 3, 5, 7. We exclude the 4th index. We have 2, 3, 5, and 7. These are the elements of this slice. And what is the length here? The length is 4. That is the capacity here. The capacity is still 6, because starting from this, we go up to the last element of the backing array, which is this. That's why the capacity is 6. Okay. And we can see here, length is 4, capacity is 6, and the elements are 2, 3, 5, 7. Now, what happens at this point? At this point, this is the backing array. Now, what happens this? Now here, this is the backing array, and we slice from this slice. We slice from this, but the backing array still remains the same. Okay. This is the backing array. What are we doing here? We are starting from the second index. So we are starting from here. Second index, we include this. We are starting from 5 and up till the last element. Now last element, not of the backing array, last element of slice. When you are slicing, we go to the last element of the slice. Okay. Now what is the last element of the slice? Is 7. That's why we have 7 here. Okay. And what is the length here? Since we have two elements, the length is 2. And what is the capacity here? Now, as we know, capacity is the first element of the array that the slice points to. What is the first element this points to? This. We start from this and we go up till the end last element of the backing array. Okay. And what is the last element? 13. So how many capacity do we have? 5, 7, 11, 13. That's why the capacity is 4 here. As you can see, length is 2, capacity is 4, and the slice we print is 5, 7. This is how it works. Now, as we already know, in this case, Go assigns the 0 value of that data type. In case of a string, it is an empty string. In case of integer, it is 0. In case of a boolean, it is false. Okay. Now, what happens in this case? What is a 0 value of a slice? What will Go assign in this case? Since we are following this syntax, so ideally, if it is an integer, s's value will be 0. Since it is a slice of integer, what is the 0 value of s? Let's run this and you can see, okay, this is what we get. For this println statement, we are getting s. If you try to print s, it is printing an empty array or an empty slice. The length is 0 and the capacity is 0. So for a 0 value slice, a slice which is declared without an initialization value, the length will be 0, the capacity will be 0, and it will have 0 elements. But the thing to focus here is the value of the slice itself, not talking about length or capacity or the print statement. The value of the slice will be nil. When we try to compare it, if s equals to nil, we get inside and we print this statement because the 0 value of a slice is nil. So now the point here is 0 value of reference types. Reference types are nil. We already know 0 value of an empty string is a string in quotes. 0 value of a boolean is false. 0 value of an integer is 0. And 0 value of an array is all the, let's say if it's an array like for integer, then the 0 value will be 0, 0, 0, 0. Okay, this is the 0 value of an array with size 4 and type integer. What is the 0 value of a struct? So let's say, okay, let's come here. We have a struct and here we have a, it's an integer, b is a string. Now, what is the 0 value of this struct? The 0 value of this struct is a 0 and b as an empty string. Basically, in case of an array and in case of a struct, the 0 value is that data structure with all the 0 values of the elements. Because an array is a fixed type with 4 integers, its 0 value 0, 0, 0, 0. In the same way, since a struct has 2 fields with a integer, b string, its 0 value is a is 0, b is empty string. In the same way, we have reference types. What are the reference types do we have? We have functions, we have channels, and we have pointers, we have slices, we have maps. And since we are talking about slice here, the 0 value of a reference type, which is a slice, is nil. It's a very important thing to remember. The 0 value of a slice is nil. Now we saw the first way to initialize a slice, which is the literal syntax. So in this case, we saw that we can declare a slice and we can initialize it like this. A, and we have integer, and we have our curly braces. We have 1, 2, 3. Okay. And we saw we can declare and initialize a slice with this syntax, with the literal syntax. We also saw we can declare a slice using var and the name of the slice and the type of the slice. And for this, the value of the slice will be nil, the length will be 0, the capacity will be 0. For this, the length will be 3, the capacity will be 3. Okay, and the value will be 1, 2, 3. We have one more way where we can initialize a slice or declare a slice is using make. A make is a function, a predefined function. Make, M-A-K-E. It's a predefined function given by Go for initializing reference types. This is something to remember. Initializing reference types only. Okay, we can use make to initialize channels, to initialize slices, to initialize maps, all the reference types that we can use make to initialize, because we have a reason to use make instead of using the literal syntax. Why are we using make? So let's see that in this example. When we initialize a slice using make, what happens? So what we are saying is we are initializing a slice of A, and we are saying make a slice. Make, you can take it as semantically, whatever it reads like. You're saying make a slice of integer. You're saying make a slice of integer, with the second argument. The second argument to the make is the length. This is how makes signature looks like. Make, it takes three things. First is the type. And what are we providing in the type? We are providing, it's a slice of integer. It is a slice of integer. Since we also use make to declare and initialize maps, to declare and initialize channels, so we have to explicitly say that it is a slice of integer. First parameter, first argument is a type. What is the second argument? Is the length. You can say what is the length of this slice going to be. Okay. Now we already know that slices are dynamically sized. We will see how the dynamically sized mechanism works. But initially, you're saying initially the length should be 5. Okay, you're saying the length should be 5. Now there is a third parameter. There is a third parameter called capacity. We already know the mechanism of capacity. We still have not gotten the exact use case of capacity, but we'll get it soon. Now the third parameter is capacity, but by default, if you don't provide the capacity, it will take whatever the length is. So in this case, the capacity will also be 5. So now we have a print slice function. What we are doing is we are printing the length, the capacity, and the slice itself. Okay. Now in the first case, what should it print? Now that we have the theory, before you run the program, we can visualize it. For the first statement, for the first print, what we are doing, we're printing A. At this point, what's the state of A? The length will be 5 and the capacity will be 5. Okay, then now let's move on to B. What's B? Okay, now we are using make. What is the type? The type is a slice of integer. What is the length? Length is 0. What is the capacity? The capacity is 5. Now, you cannot provide a length that is greater than capacity. That is an error. Okay? That's something to remember. The capacity will be always same or greater than length. A capacity cannot be less than length. Okay? Since capacity represents the size of the backing array, so capacity will always be the same or greater than length. Okay. Now, this is the state of B. Now, when we call print slice, what should it print? It should print length is 0, capacity is 5. Also, for A, I forgot to mention what will be the actual slice print. In case of A, since the length is A and it is a slice of integer, ideally it should print, A should print 0, 0, 0, 0, 0. 5 zeros because the length is 5. What should B print? It should print an empty slice because the length is 0, so we don't have any slots to initialize it with. In case of A, the length was 5 and the type was integer, so the 0 value of a slice of integer with length 5 should be 5 zeros. Okay. Now C. Let's move on to C. We have C here. Now we are slicing C from B. What are the properties of B? You have length 0 and capacity as 5. Okay. And what we are saying, we are saying for C, we want to slice from the start, from the 0th index to the second index. Now now B has the capacity of 5. B has a capacity of 5. So let's imagine B has a capacity of 5. Now for C, B is the backing array. There is another backing array, but for C, you can imagine B is the backing array. what you're saying, we are saying starting from the first index. The first index is of course 0. We want to go up to the second index. So ideally we should have 0, 1, 2. Since we exclude 2, we have 0 and 1. We have 2 elements. Okay, we have 2 elements. Now what will be the elements? Since the length is 2, we are slicing 2 elements. Length is 2 and it is a slice of integers. We should have the 0 value of 2 elements, which is 0, 0. Okay, the length is 2. And what will be the capacity here? Capacity of the backing slice is 5. And we did not slice, see, we did not slice from first index or second index. We sliced from the very first 0th index. That's why the capacity does not change. The capacity only changes when you slice after the first index, after the 0th index. Any index which is more than 0, if you slice from there, then the capacity reduces. But it does not reduce when you slice from the end. Okay, that's a mental model. You don't really have to understand or memorize, but you'll get it after you use slices a little bit more. Now, what is the capacity here? Capacity is still 5 because we did not slice after the 0th index. We sliced from the 0th index. Now, what is D? For D, what we are saying, from C, starting from the second index, it has only 2 elements. We don't really have index 2, but we have capacity of 5, so we can slice up to 5 elements, because the capacity is 5. Okay, what you're saying, 2 to 5, since 5 is excluded, we print 2, 3, 4. Okay, print 2, 3, 4, but there are no values here, so we go to 0 value. What are the 0 value of integer? We have 3 zeros. It's 2, 3, 4 for index 2, index 3, index 4. What is the length now? Length is of course 3. What is the capacity? Now, since we sliced from the start, we did not slice from 0, we sliced from 2. Now the capacity decreases. Now, so 0, 1, 2, 3, 4, we had 5 indexes. Since we slice from here instead of here, this is gone. Now we have 3. The capacity is 3. From 5, since we sliced from index 2, now the capacity is 3. Now let's try to run this program. As you can see, for the first one, length is 5, capacity is 5. We have 0, 0, 0, 0, 0. For the second one, the slice is empty. Length is 0, capacity is 5. For the second one, we have 2 zeros. The third one, we have 3 zeros with length 3 and capacity 3. As expected, the same values that we saw in our figures. Another thing to know is we can have 2-dimensional slices. A slice can contain other slices. So in this case, what we are saying, we have a slice which is a slice of another slice, and that slice is a slice of string. So we are initializing with each slice, which is a slice of string, and we are providing different strings. So this is how you declare and initialize a 2-dimensional slice. We have 2-dimensional arrays in a lot of languages, pretty much every language. In the same way, in Go also, we have 2-dimensional slices. And if we print this, we should have some kind of matrix. And as you can see, we are printing a game of tic-tac-toe. Okay, and we can change the values using the x index and y index in different positions. That's pretty much all there is to it in 2-dimensional slices. Whatever your intuition, whatever it sounds like. Initially, I said that slice is a dynamic array. And dynamic means we can extend a slice, extend its length, extend its capacity, and add more elements, remove elements, all the dynamic properties that are useful in a real world application. That's why we use slice more often than we use arrays, because of their dynamic nature. Now, how do they work? How do we actually add more elements to a slice after we declare it? So this is how it works. This is the syntax. We declare a slice, and we are using the var syntax. So at this point, the value of the slice will be nil, and if we print it, it will be an empty slice, and the length will be 0, the capacity will be 0. Okay, and if in the first print statements, we should get the length 0, capacity 0, and empty slice. What happens here? We are saying we are appending to this slice the first argument. So append is an inbuilt function in Go and it takes multiple arguments. The first one is the slice, which we want to append to the slice, and we are providing s here. What is the second argument? This is the element, the new element that we want to append to the slice, or that we want to push to the slice. And here the new element is 0. What happens? We had a slice which looked like this with length 0 and capacity 0. Append does a lot of things, a lot of calculations behind the scenes, but on a high level, the reason we are provided with this function, we are provided, first thing, it takes the slice that we want to append to, takes the existing slice. As you can see here, we are providing the existing slice s. First thing, it takes the slice, and in the second parameter, it takes the new elements. Okay, and it also takes a lot of, you can also pass more arguments into the function. It is a variadic function. Go has a concept called variadic function, where a function can take any number of arguments. Okay, now append is a variadic function. You can pass any number of elements in the after you pass the slice. Okay, now second, it can take one element like it is taking now, 0, or it can take any number of arguments. It takes two things. What it does is, first it checks the length and the capacity of the existing slice. Now what is the length and capacity of our existing slice? It is length is 0, capacity is 0. Now if that is true, and since we are trying to add more elements into that slice, but we don't have the capacity for it. Okay, the backing array that we are using in this slice, the array does not have enough capacity to it. So what append does, it assigns another memory location, another backing array whose length is 1 and whose capacity is 1, and it returns that as a return value of append. Now you are assigning it to s. Now what happens? S has length 1 and capacity 1. What happens here after that? Then at this point, s has length is 1, capacity is 1. Now this is what s looks like as of now. Now what we are doing, we are calling append again, and we are passing 1. We want to append the number 1 into this slice. We pass it, and append checks the capacity of the existing backing array. And since the capacity is 1, we are trying to insert another element. So we need at least 2 slots. So for that, append finds another memory location and it assigns another backing array. Now we have length as 2 and capacity as 2. And this is what the new slice looks like. And this is what we return, and we assign it to s again. Okay. Now at this step, this is what it looks like. And since we are inserting 3 elements, now append follows different algorithms to resize the existing slice. There are a lot of internal details there, but on a high level, there can be 2 situations. Either you are appending 1 element, or you are appending a number of elements. You are using the variadic parameter. Now to understand that, so let's go to our notepad. Now as I said, there can be 2 cases. One, you are inserting 1 element, or 2, you are inserting variadic elements. Now there are a lot of internal details, as I said, for resizing the slice inside the append function. Now we can actually take a look at how the code looks like, which resizes the slice using the append function. Now if we go here, this is actually the code which does all the resizing of the slice and all inside the Go programming language. You can see there are a lot of internal details here, and there is actually a function which is next slice capacity, the function to calculate what is the capacity of the next slice. You can see there is a threshold of 256, length of 256. If it is smaller than that, it doubles it, otherwise it does something else and all. So there are a lot of things happening here, a lot of internal details. But to have some idea about how the algorithm works, we can take a look at some of these rules. So the first rule is, if it is a single argument, if it is a single element, first thing we know, we use append to resize, to add more elements to a slice. So let's say we have a slice with length 0, capacity is 0. We have an empty slice. Now, if we call append, s equals to, we take s, we pass it to append, and we add another element, let's say 1. What happens now? What append does, in this case, since this is a single element, what append does, since the capacity is 0 at this point, it checks the size of the element, since this size is 1. So append finds another memory location for the new backing array, and it finds the pointer to that, and it assigns that new pointer. And that array will have a length of 1 and a capacity of 1. The first time we call append on an empty slice. What happens the second time? Now, this is what the slice looks like. We have 1 here. Length is 1, capacity is 1. What happens if we call append again? We call append again with s and number is 2. At this point, what happens? It finds, since the capacity was 1, we are trying to insert another element, so we need the capacity of 2. So it finds another memory location for the backing array, and it assigns the pointer to that, to the new slice, and now the length is 2 and the capacity is 2. We'll soon notice the pattern here. Again, let's try to append another element. Append s, and this is what the slice looks like in the previous step, 1, 2. Now s3. Now at this step, what append does? Since we have capacity of 2 and we are trying to insert another element, now we need slots for 3 elements. Now what append does? It tries to find another memory location for the backing array, and the length will be now 3, but the capacity will be the double of the previous one. So previously we had capacity of 2. Now we will have the capacity of 4. Okay, so let's do one more time, then we'll see the pattern. Let's call append, then s, then we pass 4. Okay, and this is what it looked like, 1, 2, 3, and we call it once more. Now we had capacity of 4. Now we are trying to insert another element. We only have 3 elements as of now. So the append does not do anything. It has enough capacity to assign one more element. So now length will be 4, capacity will be 4, and this is what the array slice will look like, 1, 2, 3, 4. Now what happens here? One more time. Call append, call s with 5. Now we have 4 elements, we have capacity 4. We are trying to insert one more element. Now we don't have the space for that. Now what append does? Now the length is 5, capacity is 8. It is 8, and this is what the slice will look like, 1, 2, 3, 4, 5. Now we can see the pattern. When we are trying to insert single elements, append will try to double the capacity every time there is no space. Every time there is no space, it will try to double the capacity up to, as we saw here, up to the threshold is, up to the length is 256. After that, it will, as it is written in the comment here, it will, instead of 2xing, it will go in the 1.25x speed. It won't double it. It will go in the speed of 1.25. Up to, it will only double it up to the length is 256 elements. After that, it will go 1.25x speed. It won't double the capacity. That is an internal detail. Now, that is one pattern. And if you want to see an example for that, here we are declaring a slice with 0 value, and we are starting a for loop. And in every iteration, we are appending the index into the slice. And then we are printing the length and the capacity of the slice in the print statement. Now let's run this, and we'll have a fair idea how the append works behind the scenes. Okay, now if we expand it, okay, let's focus here. Let's focus what's happening. In the first iteration, the length and capacity was 0. So append made length 1 and capacity and 1, and this, it is 1. In the second iteration, it inserted another index, and now the length is 2, capacity is 2. in the next iteration, when it was inserting, let's say first 0, then 1, then 2. When it was inserting 2, obviously the space was not enough, so it doubled the capacity. From 2, it went 4. Okay. Now, in the next iteration, it has enough capacity. It has the capacity of 4. So it can store one more element. So that's why we can see the capacity does not change until this. The length is 4, the capacity is 4. Okay. Now in the next iteration, when we are trying to insert the index 4, now it does not have the storage anymore. Now it needs to increase the capacity again. What it did, it doubled the capacity again. The append function doubled the capacity of the internal backing array. Okay, that's what's happening here. Now we can insert 4 more elements. Up until this, we had 4 elements. Now it doubled the capacity, so we can insert 4 more elements. Now at this point, we have 8 elements and we have capacity 8. As you can see, the length is 8, the capacity is 8. Now append has to assign a new backing array. It has to increase the capacity again. Now it doubled it. From 8, it went 16. Now after this, we can insert 8 more elements. We had 8 elements, it doubled the capacity, and now we can insert 8 more elements without append having to increase the capacity, without append having to assign a new memory location. It can store the elements in the same memory location. So as you can see, length is 10, 11, 12, 13, 14, 15, 16. Now when the length and capacity matches, the capacity is doubled again. So this is the pattern you can see. Every time length and capacity become same, in the next append call, the capacity doubles. Okay, that's the formula. Every time length and capacity matches, in the next iteration, append will double the capacity and it will assign a new memory location for the slice, for the new backing array. And now why am I trying to explain these internal workings of how append actually works? What is the need of it? Because most likely, this is how you'll use. You have an slice and you call append again and again. Every time you have to add more elements. You never have to think about what is the capacity, what is the length and all. Those are internal details. You will never actually have to explicitly think about the capacity and all. The append handles all those details behind the scenes. But the reason I explained it, the reason I explained how it works, what are all the things that happens behind the scenes every time you call append, every time the length and capacity matches, is because let's take an example. Up until this, let's print the value of this. Let's clear this. Row, go, run, main node, go. We have length 0, capacity 0, and there is an empty slice. Now, when we try to append another element to this and we call print slice again, now what happens? Let's run this and we can see that length is now 1, capacity is 1, and we have 1 element in the slice. What happened behind the scenes? Append checked the capacity and it realized the slice, the backing array, does not have enough capacity to store 1 more element. So it searched for another memory location and it found another location for the new backing array, and the new backing array has capacity of 1 and length of 1. And as we saw earlier, if you call append again, it will do the same number of steps again, and the length will be 2, capacity will be 2, and it will keep reallocating. It will keep reallocating and finding new backing arrays. Every time you call append, it will try to double the capacity and it will try to do all those optimization steps to resize the slice. And all these internal calculations will keep happening when you start with a slice of 0 length and capacity. But let's imagine there is a scenario like this, when you know beforehand that you want to append to this slice 5 times. You know this information beforehand. And in this case, if you initialize with an empty slice with length 0 and capacity 0, and you run the iteration, it will work. It will definitely work. And if we can run this, and when we run this, we can see that it started with length 0, capacity 0. Then in the next iteration, capacity is 1. Next capacity is 2. Then capacity is 4. And then the capacity is 8. Okay. And every time you know that length and capacity matches, every time length and capacity matches, in the next iteration, the append has to do all these internal calculation. It has to find a new memory location. It has to find a new backing array with a double the capacity in all this extra work. Every time reallocation happens because of the shortage of capacity. Now, if you know the maximum length that this slice can have, what you can do, one optimization that you can do to prevent append from doing all this extra work is this. Instead of initializing s like this, what you can do, you can remove this and you can use the short declaration form, and here you can use make. And you already know, if you use make, we can define a length and an optional capacity. Let's say we want length as 0 because we don't want pre-filled zeros inside the slice. Because if you define length as 5 and capacity is 5, it will pre-fill all those places with empty zeros. We don't want that. That's why we are saying length is 0, but capacity is 5. Maximum we'll have 5 elements, but for now, give us an empty slice. What happens if we run this now? Now, as you can see, the capacity from the first iteration is the capacity is 5. And we keep appending to it, and up until the last iteration, the capacity remains the same, because we already knew that we are going to append 5 elements max. And we just prevented append, the function, inbuilt function append, from doing all those extra calculations every time there was a shortage of space. So this is something you have to remember, that we'll use, especially this syntax, that if we know beforehand what is going to the maximum size of a slice, we can use this syntax to pre-assign a capacity beforehand to prevent append from doing all the extra work every time it runs out of space. Go provides us one more construct to loop over slices. We have a traditional method where we use a traditional for loop. We initialize a variable, we put a condition, we do increment in each iteration, and then we can print the index and the value using the index access method. This works. But Go provides us another construct. This is called range. And using range, you write a for, and with each iteration, Go returns 2 values. The first one, the index, and the second one, a copy of the value. Not the value itself, a copy of the value. This is something you have to remember. If you make any change to this value here, it won't show up in the original slice because this one is a copy in each iteration. And you can access the value of I and B here. And if we try to print this, we'll get this 0, 1, 2, 3, 4, 5, 6, 7. And if you don't want to use the index, then you can use the underscore. And if you don't want to use the value, you only want the index, then you can leave it apart. Okay. And if you want to take a look at some examples of slices in real world apps, then we can take a look at Spider. And we can see we have a lot of use cases. Here they are using the slice literal syntax to directly declare and initialize a slice in the same line. We have some make based syntax to initialize a string slice with length 31 and capacity 31. And similarly, there are a lot of use cases everywhere in the code. Slices are one of the most common used data types in Go, and you will see a lot of examples everywhere. Okay, here we have a range over slice. They're accessing the value of title in each loop, and they're doing something with it, and a lot of examples like that. Now the next data type that we have is maps. Go offers a implementation of the data type hash map, which are also called dictionaries, hashes, hash maps in other languages. Go also has a similar implementation. It is called map. And map, a typical structure of a map is it has a key, which is mostly string, but you can also use other data types as the key. And it has a value, and inside the value you can store anything. Okay. Maps keys has to be comparable. So comparable basically means they have to satisfy the equality operator, so that a map keys can be compared with each other. They have to have that property. That is one restriction of maps keys. And in the value, you can store anything in a map. Okay. And usually we use map whenever we have a use case where we want to find things quickly. That's the mental model you should have. A lot of people get confused with when to use struct and when to use map. Struct is your typical use case whenever you want to store something, whenever you want to parse data from a JSON. A lot of use cases. In pretty much 70% of the time, we use structs. Struct are for storing values, for efficient storing values in the format of Go's native data types. In map also, you can store values, but we use maps when we want to find things quickly. Okay, because maps have the lookup time of one, lookup time and adding time and deleting time. All these, it's a very efficient algorithm to look up things and to add things and to delete things. That's the reason we use hash maps or maps in Go to perform those kinds of tasks. Now let's understand with an example how they exactly work. So what are we doing here? We have a struct, we have a type struct, and it has two fields. One is lat and second is long, one for latitude, one for longitude, and both are of type float64. Okay, this part we already know. Then we are declaring a variable in the package level with using var syntax. The variable name is m and it is of type map. A map with key as string and value as vertex. So whenever you are declaring a map type, you have to explicitly say what is going to be the type of the key and what is going to be the type of value. Now here we declared a map. Now as we already know, map is a reference type and every reference type has the zero value of nil. So at this point, m's value is nil. Okay. Now here what we are doing, we are ignoring whatever the zero value is. We are using make. As I said, every reference type can be initialized with using make. So we are using make to initialize a map. We are not providing any length, capacity and all. We are just initializing a map using make. Then using this index-based syntax, we are storing a struct's instance. A struct's instance, a struct of type vertex, we are storing this struct in the key bell labs. Okay, this is how you store things in a map. And then we are printing it. And if we run it, we get the value of the struct. Okay, that's how maps work. You initialize a map, you store things in the keys, and you can access them using this index-based syntax. This set and get pretty much looks the same way. Now there is another syntax of initializing maps. Instead of using make, you can also use the map literal syntax. Map literal syntax basically means you just write the type and you provide the initialization value right away in the same sentence. So we are saying we are declaring a map whose key is string and the value is vertex, which is of type struct, and we are providing the keys and the values, in the same line. Okay, this is another syntax to initialize maps without using make. How do you manipulate values and keys? How do you manipulate keys and values of a map? We have some of the features provided by Go. As you know, we can initialize a map using make. And also, one thing to remember when using maps are, you only have two ways to initialize maps. First, you can use the make syntax or you can use literal syntax. Third, if you try to initialize a map using var, which we do with other data types like integers, strings and slices and all. If you initialize a map, declare a map using var syntax, and if you try to assign a key in that map, then you will get an error. You will get a panic. You only have two ways of declaring a map. Either use make syntax or use a literal syntax if you know the initial values already. Okay. We can actually see this. In this example, as you can see, I have declared a map using var syntax. Okay. As we typically do with other data types like slices and integers and booleans and strings. I've declared the map using var syntax and then I am trying to assign a key to the map. Since it's a the key is of type string and the values are of type integer. I'm assigning key 1 the value of 9. And then I'm trying to print this. Then what happens if I try to run this? We get a panic. We get an error that assignment to entry in nil map. Since using var syntax declares the 0 value of a map, and the 0 value of a map is nil. That's why we get this error that assignment to entry in nil map. What can we do in this case? We have two choices, as I said. Either we can do this, we remove the var and we do short assignment, and then we use make. Then make, and then you do this, and then we try to run this. Then we get the appropriate behavior. We have a map and the key 1 key has the value 9. We have one other choice. We can do this. If you don't want to use the make syntax, we can write the type, then we can provide a curly braces. This is the literal syntax. Okay. And if you try to run this, we get the similar behavior. So as I said, when using maps, either use make or use the literal syntax. Those are the two choices that you have. Never use var to declare a map unless you know exactly what you're doing. Okay, now we have this example where we are looking at some examples of manipulating the keys of a map. Now here we initialize a map using make. And since we are using make, we are safe to assign keys to the map. Now we are assigning a key answer and we are assigning the value 42. Now we are assigning this another value to the same key. And let's try to run this, how the program behaves up to this point, up to the point here. And let's see the behavior. Now if we run this, so first we have the value 42 because we assigned 42 here to the key answer. And in the next print statement, we are assigning 42 and we can see the value 42. Then what happens? We have a predefined function called delete. And using this, we can delete values from a map for a particular key. So when we delete a value and then we try to print the value for that key, we'll get the 0 value of that type. Since it's an integer, we are getting 0 here. Now, the question here is, how do you know that whether this key answer has the value of the number 0 or the value is absent, the value does not exist? That's why the Go language is giving you the default value 0. How do you differentiate between the absent value and the 0 value? That is the question. So for that particular use case, Go provides this construct. You can try to access this value of a map using this syntax, the index-based syntax, which returns two values. The first one is the value. If the value exists, then you'll have the value here. If it doesn't, it will have the 0 value here. Then it also returns a boolean, and you can name it anything. The convention is to name it OK, so that other engineers are also aware that you are checking the existence of this value. Now we can, if the OK is true, then we'll know that the value exists, and whatever the value, even if the value is 0, we know that it exists and that is meant to be the value. It is not an absent value. It is not a default value. That is meant to be the value. 0 is the value of the key answer. If it is false, then we can ignore the value and we can proceed further with whatever the expectation is. We can know that the value is not set for this key. And that's pretty much all about maps. We can do other things with a map. For example, let's say we have this, and let's remove this. And what if we want all the keys and values of a map? So we can use the range construct that Go provides to loop over slices that we can use for maps also. So let's say we write for, in the first result, it will give us the key, then it will give us the value. And in the short declaration after that, we write range, and we want to range over M. This is a map. And here we can print this fmd.println. We can write key comma value. And if you run this here in the last print statement, as you can see, the key is answer and the value is 42. And using this, we can range, we can loop over maps, and we can access all the keys and values. If you don't want the key, you can use the underscore identifier here like this if you only want the values. And if you only want the keys, then you can get rid of that part. Now this is how you iterate over a map. Now another